Hi, my name is Antonia Panella, and today I will be discussing single-camera high-speed stereo digital image correlation using an X-cube prism. Digital image correlation, or DIC, is an optical measurement technique where successive images are used to determine the deformation of an object. DIC is a non-contact form of measurement, making it a valuable tool for determining the mechanical properties of complex geometries. In 3D DIC, two cameras in a stereo configuration image a specimen from two different angles. This set of images is known as a stereo pair. A stereo pair of images is used to determine the position of the specimen relative to the cameras. In doing so, 3D deformation of the specimen can be determined. 3D DIC can be performed using high-speed cameras. Using high-speed cameras offers valuable insight into the damage and failure of advanced materials. Advanced materials include laminated hybrid braided composites. Braided composites are materials composed of an interwoven structure within a resin matrix. In laminated hybrid braided composites, different materials are layered together for superior properties over braided composites composed of only the individual constituents. However, high-speed 3D DIC is challenging to perform given that high-speed cameras are exceedingly expensive, making acquiring multiple cameras difficult. In addition, synchronizing multiple cameras running at thousands of frames per second is challenging from a technical standpoint and requires specialized equipment to do so. To mitigate these barriers, a single-camera stereo DIC setup was designed for this project. In the proposed setup, two different perspectives of a specimen are reflected into an X-cube prism. X-cubes are prisms composed of red and blue reflecting dichroic filters in an X configuration. In this configuration, only the red or blue light from each perspective can be reflected and recorded by the high-speed camera as a single image. The combined image is then divided into red and blue sub-images by a post-processing algorithm serving as a stereo pair. The proposed setup was designed to be able to image specimens for various mechanical tests, accommodate a V1611 Phantom high-speed camera, and be versatile and accommodate a variety of optical equipment and configurations. For imaging, the setup is composed of two 3-inch mirrors, a 50mm X-cube, and a V16 Phantom camera with a Nikon lens. To ensure versatility, this equipment rides on 95mm optic rail and can be adjusted. In addition, the plate holders for the mirrors and central platform are general use, so different optical equipment can be substituted if required. To ensure that the acquired images are high quality, the setup sits on vibration isolation legs to prevent movement during imaging. During testing, the setup sits on a table in front of the specimen to be imaged, making it adaptable to many types of mechanical tests. To ensure that the intensity of the red and blue sub-images are equal, imaging will need to be conducted using red and blue light sources. Imaging using the proposed setup is advantageous given that spatial resolution is preserved, since the blue and red channels of the acquired images are used as a stereo pair. In addition, the parts for the proposed setup is only 16% the cost of purchasing an additional high-speed camera. Having to correct for color crosstalk is a limitation associated with this setup. Since high-speed cameras use only one sensor for creating images, the spectral response between the three color channels overlap. As a result, images may have noise and errors in coloration, diminishing the quality of the acquired images. However, this can be mitigated through color calibration and crosstalk correction. In color calibration, the specimen is illuminated and imaged using either just a red or blue light source. These images are then used to create calibration correction equations that, when applied to uncorrected images, will remove the intensity within the images associated with crosstalk. For ease of processing, a crosstalk correction GUI, or graphical user interface, was created that automates this process. In future testing, imaging will be performed using the X-cube method and will be compared against the results of conventional two-camera DIC imaging to demonstrate the validity of this method. Once the X-cube method is fine-tuned, it will be used to image hybrid laminated braided composite samples undergoing impact pendulum testing. In doing so, the mechanical properties of these materials will be determined. The hybrid laminated braided composites will be composed of Kevlar and carbon fiber. In conclusion, single-camera stereo DIC methods, such as imaging using an X-cube, enables high-speed imaging to be more accessible for both industry and academia. Thank you for listening. I would like to thank my lab mates and supervising professor, Dr. Garrett Malenka, for helping me with this project, and Laura for providing me funding to do so.